And the remainder of this little lecture will be about what happens if you have an exact sequence and you start applying functors to it, because maybe what comes out, of course you have to end up in a category where you can talk about exactness, so it has to be something like S modules for some ring S. But then what comes out may or may not be an exact sequence, and this happens a lot that is not exact, but we introduce some terminology and give some examples that show up a lot. Okay, so let's go back to exact sequences. Yeah, so let me make one remark that I could have made in the first bit, but then sort of forgot, but I didn't want to interrupt that stage. So if I have the sequence so this is exact at AI. Well, you can write this down in another way. That's the same as saying that 0 goes to the image. Okay, I need my notation, phi I plus 1, phi I, image phi I plus 1. So this is a submodule AI. Then I map this to AI, this is the natural inclusion here, and then I map it to the image of phi I. So that's just what you do by applying phi I, but then of course you end up in the image of phi I in here, and this is always going to be a surjection. So I claim this is exact at AI, if and only if this one is short exact. Now, as I indicated, this with the natural map phi I is always surjective. This is just a submodule, so this is always injective. This is really a statement about what is happening here. So then you should realize that the kernel of this map, well, this is just the same map as phi I, but then sort of restricting where it goes to, but the kernel is exactly the same. Okay, so the kernel here is exactly the kernel of phi I, and that should be exactly this submodule, okay, because this is in itself equivalent with saying that the kernel of AI to the image of phi I, which is always the kernel of phi I, so that's the kernel here, and that should be the same as the image of phi I. Right? So if I say this is exact, and I really mean this equals that, but if you observe that this equals that always, then it's clear that exactness of AI is the same as saying that this thing is exact here. So that means that in a way you can check whether something is exact if you have a long one by breaking everything into short exact sequence like this. Okay, so that is very important, because that means that if you're talking about the exactness of, say, very long sequences, you can reduce everything to something about short exact sequences. Okay, so we'll now be talking a lot about what happens with short exact sequences. So let's say that we have a functor from a category C to D. And I'll be a little bit vague in the sense that the notions what I'll be writing down will be very general, but we should simply stick to what we have here. Say C, for example, would be left R modules, and maybe D would be left S modules, where S is another ring. Okay, suppose we have something like this. And then we can introduce some terminology. Okay, but I need to be able to talk about the notion of an exact sequence in both C and D. So we need enough for that, say, modules over some ring. So suppose we have that, and we have 0 goes to A prime, goes to A, goes to A double prime, goes to 0, a short exact sequence. In C. Okay, and then we say that F is left or right exact if, it depends a lot on whether F is co or contravariant. So let me just do the four cases. It can be either left or right exact, or nothing, of course, and F can be co-invariant, can be contravariant or not. So let me make a table. Left exact, right exact. So if the statement will be called left or right exact if the sequence that I will be writing down in this table is exact in the appropriate case. So here we have F covariant, and here we have F contravariant. And so let me do the covariant first, so that means the errors don't reverse. So here I apply F, and of course 0 has to map to 0 under kind of function we're talking about. Then I just apply F to the exact sequence. And I accept that I don't get the surjection here, if we think about error modulus, so exactness here may be lost, but on the left-hand side is preserved. So this will be left exact, F covariant. And if you go about right exact, then you accept the loss of the 0 here, but not on the right. So in that case, I want to have F A prime goes to F A goes to F A double prime goes to 0. And for contravariant, you basically do the same thing, but of course the errors will change. But if I want to have left exact, then I want 0 in the left on the result. So I should get 0 goes to F A double prime goes to F of A, and this goes to F of A prime. That's similarly here, but then I want 0 on the right. Okay, so it is left or right exact according to whether, depending on the table, if F is covariant or contravariant, the corresponding exact sequence that I wrote down is exact. Okay, now it will also be if your functor F is really nice, if it satisfies both left and right exactness. And you can check. And in fact, I say I would suggest to really do it, because so what does it mean? That means that if it's both left exact and right exact, for example, if it's covariant, then this will be exact because it's left exact, and this will be exact. That means that if I simply put this surjection to 0 here, then I get exact. So it transforms a short exact sequence into a short exact sequence. And the same thing with contravariant, but the errors have been reversed. And as I mentioned, you can check whether you have a long exact sequence by sort of looking at a lot of short exact sequences. Well, that means that if you have functor F, which is both left and right exact, so as I indicated, it will preserve short exact sequence, in the sense that if I apply F to a short exact sequence in C, I get one in D. And then I can play the same game again, going from the short exact sequences I have there, but then in D, and then sort of putting them back together again to a long exact sequence in D. So if you work this out, you see that F is exact if and only if it transforms. So applying F to an exact sequence and C always gives an exact sequence. Okay, so even though everything is really defined on short exact sequences by this remark, you can then put everything back together and notice that we really preserved exact sequence, or transformed an exact sequence in C to one in D. So let me just give examples for the remainder. And well, I basically indicated there are 4 cases. So I'll be first giving 4 examples more theoretically, and claiming that that indeed what comes out is left, right, exact, etc. And leaving lots of details to you to fill in. And then I'll actually do some calculation to show what is really going on in more explicit cases. Okay, so let's see what we can do. Examples. Let's first do the covariant ones. So the first one will be, so B is a left R module. And I take F from R modules to appealing groups, and I'm actually not sure where I just add or maybe I should write Z modules, but anyway, category of appealing groups. And I can take an arbitrary R module A, and then I can apply home R to A, and just look at all the R module homomorphisms of B to A, and as Arno Kret indicated, this is itself going to be something that has an addition because A has an addition. And I claim this is left exact. Okay, so let's see, it should be covariant. So if I start with a bunch of A's, fortunately you have the same notation here, and well, let me check this one, this injection. If I have a map from B to A, so I can think of a B to A prime here, and if this map, then my map from F A prime, so home of B to A prime, this is an element, I go to this one by composing. I have this map from A prime to A, and by composing I get my map from B to A. Now suppose I get 0 here. Well, that means that this map here is a 0 map. But because this is an injection, that meant that this was a 0 map. And indeed, therefore, the kernel of this map is trivial. Well, you can check like this all the time, but indeed, if I start with a short exact sequence of R modules A like this, for A prime, A, and A double prime, and I use this and get a functor, so home, I have been interchanging my A and B, I think. No, sorry. No, that's okay. Actually, right, so the F is applied to the A, so this is okay. My B is fixed. So you can check that indeed, in that case, home B to A prime for a fixed B, to home to B to A, and then to home to B to A double prime. This is going to be exact with this one injected. But it may fail to be right exact, as we'll see in the example later. So let me do the second one. So covariant, this one is left exact, so that was the first one. The second one will involve the tensor product. So now B is going to be a left R module. And A, this will be a right R module. And then I claim that if I take the functor from the right R modules, to, again, the Boolean groups. And I take A, and I bring this to the construction in first my other lecture on tensor products. I can take this tensor product. A is the right R module, B is the left R module. So this is just going to be in group a Z module. I claim this is right exact. Okay, so let me just make it explicit. If 0 goes to A prime, goes to A, goes to A double prime, goes to 0, if this is exact in the category of right R modules, and I have a tensor everything on the right with R, then I get A prime tensor R, sorry, on the right with B, goes to A tensor R with B, goes to A double tensor R with B goes to 0. This is exact in the groups. And so this is rather easy to show in the sense that, well, for example, this here, the image here will be contained in the kernel of this, because if I go from here to here to here, then, well, you just apply the maps here on the first coordinate, and if I do this twice, I get 0. So everything here maps to 0, tensor, whatever, and that was 0. To show exactly that the kernel here is exactly the image of this guy is a bit more tricky, but it's a good exercise to show this from the definition of the tensor product. Again, the surjection here is not so difficult because, well, you just apply from A to A double prime basically, and you have tensor with a B on the right, and this is surjective. Okay, so those are two examples. Let's go contravariant. And say for 3, let's take B, a left R module, and then I can go from left R modules again to Boolean groups. And I take an A, so this will be F, and I take an A, and I take this hom R, A, hom as left R module. So this looks a little bit like this example, but there my B in the first coordinate is fixed, and the, so that the variable, the objects in the category were in the second position, but here I have reversible the A and the B, and now it goes from covariant to contravariant. So I claim this is going to be left exact, i.e. if 0 goes to A prime, goes to A double prime, goes to A, sorry, A goes to A double prime, goes to 0, is exact in the category of left R modules, then 0 goes to hom R A double prime, B goes to hom R A B goes to hom R A prime B is exact. Okay, so the maps are, for example, if I have a map from A to B, right, so an element in here will be a map from A to B, then I can compose from A prime to A to B, and that will be the image here. So this map comes from composition with the maps in the sequence. And again, it's a bit of a chase of the diagram to really check that this is going to be exact. And again, it can actually go wrong on the right-hand side. It may not be subjective. And then the last one, 4. And I must say, I found this example slightly artificial. The other 3, so if you just work in, say, mathematics in a particular field, you just run into. This one I more or less had to construct. So let me just say it is artificial in a little bit. Of course, it does show up, but maybe not the first thing you get. I go from abelian groups to abelian groups. And I take an abelian group A, and I'm going to do 2 things to it. So first, I'm going to take home of A into Q modulo Z. That's the first thing. And so this is essentially of this type. So this will be contravariant. But this is actually an exact functor at this stage, because this Q modulo Z is divisible, and it's maybe not so easy, but a very interesting exercise to show that if I take abelian groups, I take a divisible abelian group, then the functor hom Z, well, mapping A to hom Z A divisible abelian group is actually exact. In that case, you get a full exact sequence, short exact sequence here. But it's not what I want, because I want to have something that is right exact but not left. And then I can tensor it. Let me write it as follows. So this is a Z modulo abelian group. So I can tensor it with, say, Z modulo 2Z. And I already wrote down the example here. Tensoring is in general only right exact. So the first one reverses the order, and then I impose this one. So this is right exact. Okay, and I think I'll just want to finish by computing some examples of this. So I just take a specific A and B, and then you see a little bit better what's going on. So let me compute the examples. Always in the category of Z modules, which is the same as abelian groups. And always starting from, okay, I erased it by now, but I defined left and right exact by starting with a test sequence. 0 goes to A prime, goes to A, goes to A double prime, goes to 0, and that will be this one. And that is the example I had before, the even integers Z multiplied by 2, including in Z, and then the quotient Z modulo 2Z. That's the test short exact sequence. And then okay, so for this first example I wrote down, we apply hom Z modulo 2Z into the thing that we have. Well, I always get a 0 here. Hom of anything into Z will be 0. Then if I try to apply a homomorphism, if I want to map as a group homomorphism Z modulo 2Z into Z, I only get a 0 map, because Z, the only torsion in Z is a 0 element. So this is going to be hom of Z modulo 2Z into Z. The same thing will apply there. But here, I get hom as abelian groups of Z2 to Z2, and there are 2 elements in there. So I get this one. Okay, and I claimed that it was going to be left exact, and that's correct. This is still exact, but it's no longer right exact, because this map is not surjective. So the second one, we now apply tensor over Z with Z modulo 2Z. And well, if I tensor 0 with this thing, I get 0. Let me first write down what we officially get. Z tensor over Z modulo 2Z. And I told you that such a thing, I can compute R tensor R modulo B is this B, so this is Z modulo 2Z. The same thing here. And from the exercise that we've been given, that I gave you, this is also isomorphic to Z modulo 2Z. But then the, excuse me, I'm having the wrong thing here, because I don't want that one. I claimed that it was going to be right exact. So this is Z tensor with that. And well, then you have to figure out what the maps are. If you figure out what you're doing, we're multiplying by 2 here, and if you follow what you did, then you see that also multiplication by 2, that means this is the zero map. And if you follow along here, you see this is the identity map. So it's surjective, and you never see the kernel here is indeed 0, the image here, but this thing is not an injection, so it's no longer left exact. Okay, for the third example, I apply home Z into Z modulo 2Z. And so I'm claiming that the following should be exact. Okay, so in this case, all the errors are reversed. So the right-hand term in my test should the exact sequence here now gives me the left hand, and then I get home Z. And out of space, I'm going to bend the sequence. And then you have to compute what this is. Those are very easy because here I just choose an element. So this is Z modulo 2Z. This is Z modulo 2Z. And here there are also 2 elements. So this is isomorphic to Z modulo 2Z. And then, well, you can check it again in this particular claim that this is going to be an isomorphism. It has to be an injection with 2 elements. And then you will find that this is actually the zero map. Okay, so it's no longer surjected.